this talk. We are extremely pleased to have Mike Betancourt here today as part of our PRISM and CBS joint faculty search. And Mike comes to statistics via physics, which is kind of awesome. We love to steal physicists away. And is now a postdoctoral research associate at work. And he's going to talk to us today about Hamiltonian Monte Carlo.
Cheers. Thanks, Jennifer. So this is really much focused on the data science aspect of things, so it's going to be pretty high level. But if anyone wants to get into the details, the math or the particulars of the computation or coding or anything like that, don't hesitate to ask. I've got plenty of backup slides, and I think we have some whiteboards over there we can get into the details. So don't hesitate to ask before or after, or try to contact me afterwards. So I think that the main thesis I want to get at in this talk is that we have this preponderance of data these days, and this has really driven the growth of data science. We have all these wonderful database technologies. Everyone's talking about how much data they have and kind of bragging about the size. But the data that people are collecting is nasty, right? If you look at a real data set, it's corrupt, it's structured, it's missing things. We're not collecting IID replications of very, very simple processes. And so that means when we're talking about doing realistic data science, we need statistical methodologies that can capture that structure. And we need the tools that can support those methodologies and allow us to implement them in practice. And that's what we're talking about today. So Bayesian inference is going to be the methodology, the framework for really trying to capture this very rich structure in a very generic fashion. And then Hamiltonian Monte Carlo is going to be this very, very critical algorithm for building these Bayesian analyses in high-dimensional complex problems. And I want to talk about how it's really uniquely suited to pushing us into this new regime. And then I'll talk a little bit about Stan, which is our software package that wraps all of this together and really allows us to do some novel analyses. Now, to kind of ground everything into context, I'm going to use this particular epidemiological example. This comes from an analysis I'm doing with some colleagues in Imperial College, where we're trying to really understand how we can fight malaria, right? Malaria is one of these devastating diseases. Hundreds of millions of people get affected over Africa and Asia. It's really debilitating. It's a really, really nasty problem. And this is a classic example of where we'd like to bring data in to start making more informed decisions as to how we should be tackling this problem, right? Millions of lives are on the line here, and billions of dollars are in play. So we can't just try everything. We need to make very, very informed decisions as to how we should be intervening and trying to deploy these vaccines. Now, I just want to make a point. I'm not an epidemiologist, right? Up until about a year ago, I didn't know anything about malaria. This is just a nice example of the complexities that we really see in realistic problems and the kind of challenges that we need to surmount if we want to be able to solve these problems in any kind of success. Now, one of the things that makes malaria particularly challenging to vaccinate against, to fight against, is that it's a very, very complex parasite. The typical life cycle, just a very simple cartoon of what happens, is that we have some host over here, typically a human, but it could really be any mammal. And there's a particular kind of malaria parasite that infects this host. Then a mosquito comes by, gets hungry, and wants to feed, right? And so it feeds on this blood, right, filling it up its gut. And then in the gut of the mosquito, those parasites start reproducing and form eggs. Right? These eggs then propagate up to the proboscis of the mosquito. And this is a really devastating little trick it has. It turns into these spores, and it literally fills up the salivary glands. And so the mosquito goes to feed again. The first thing it has to do before it can feed is just to inject, just to vomit all of these spores into the new host. So it's this just incredibly devious mechanism for ensuring that the parasites get to a new host. Once the uninfected individual has been infected with these parasites, they go to the liver and they just produce millions of parasites. Just an exponential amplification. So you get this very, very powerful feedback cycle where now we have a new host who can then propagate the malaria further. And you can kind of see the challenge here, right? Like we could try to intervene here. We could try to limit the ability for mosquitoes to pick up the parasites. We could try to prevent the mosquitoes from being able to propagate malaria through its various stages. Or we could try to prevent the mosquito from infecting new individuals, right? There's lots of ways that we could try to tackle this. And we could try to tackle it with nets, with malaria medicines, or we could try to vaccinate. And the vaccinations are what our group particularly works on. So if we want to be able to make an informed decision as to how to tackle this problem best, we need data that captures all of this structure. Right? Observational data is not going to quite be enough because we're not going to be able to get at, every one of these stages. So what we're using here is mouse analog systems. So we basically just replicate this whole system using mice and mosquitoes instead of humans. Turns out there's a lot of ethical issues with experimenting on humans. So we start with an initial mouse, pretty standard laboratory rat. We infect it with malaria, so now it has some initial density of these parasites, and we're going to try to measure that. We then let mosquitoes feed on these mice, of course suck up that blood, start forming these eggs in their gut. Then we let these mosquitoes incubate a little bit so that those eggs turn into the spores, and then finally we allow those mosquitoes to feed on naive mice that have not been infected, right? So they only pick up the parasite from the mosquitoes themselves. And the idea is to carefully measure the parasites at every one of these stages. Right? If we have a handle on how the malaria is actually propagating, we can start constraining what's going on in this process. In particular, we can start cycling through this. Right? We can take these final mice and use them as a new experiment, use them as the initial mice in a new round. This starts letting us figure out the generational effects of what's going on. And then, of course, we really want to do this for the different treatments. So we repeat this analysis for controls, for different vaccines, different vaccine combinations. And this really starts giving us a data set that's sensitive to the effects of these treatments, right? And this would be really the minimum requirement for starting to make very sophisticated decisions and recommendations for interventions. Now, one thing we do have to be wary about here is that this data set isn't that good, right? There's a lot of variability in this process. There's a lot of variability in how much parasites the mouse might have originally. There's a lot of variability in how the malaria propagates at every stage. It's one of these exponential amplification processes that's really, really delicate. And so if we want to make better decisions, we need to quantify that variability, which means we're going to need multiple mice. So instead of looking at one mice, we're going to look at whole populations of mice, let the mosquitoes feed on these. And again, if we're careful and we capture that structure, this should give us something that we can use to quantify all the variability between these stages. So when we put all this together, we have exactly the data set that we want, right? It's sensitive to the different treatments. It captures the variability. It captures each of the stages of the transmission of this parasite. It really should give us the ability to learn everything we want to. The challenge is that this is a really, really messy data set, right? All of the structure that we needed to learn what we want makes this incredibly complex. In particular, one of the most ubiquitous properties are really, really nasty uncertainties. In particular, we run into these things like non-identifiabilities, where this data doesn't tell us that there's one set of parameters that are best. Instead, we get kind of our uncertainty distributed across the entirety of this space in these very, very complex ways. And what this ultimately does is it makes decision-making very, very challenging. So imagine, for example, that we wanted to make some kind of point estimate, right? Your kind of standard, simple first-time analysis. And the challenge is that there's going to be surfaces that are entirely compatible with the data, right? The data can't discriminate between this point, this point, this point, this point. Any point of the surface are just as good according to the data, right? These are kind of classic nonlinear non-identifiability. And so if you make a point estimate, here or here, they're just as good, right? Any of these point estimates are fine, but they can lead to very, very different decisions, right? Point Q might say, go with treatment A. Point Q prime might say, go with treatment B or C, right? We can get a whole spectrum of decisions, and the one we end up with is sensitive to the arbitrary factors that chose Q over Q prime. That's very, very fragile decision making. If we want to make robust decisions, if we want to make really good inferences out of these data sets, we need to take account for all of this uncertainty, right? We need to consider all of the parameters in this space that matter. And one of the consequences of this is that when we're talking about what are the problems in data science and statistics and data analysis that are really challenging and matter, it's not just about the size of the data. Right? The zeitgeist of big data is an incomplete characterization of the problem. If we're talking about where the challenges lie, we have to consider not just how much data we have, but also how complex of a model do we need to capture the structure in that data. So we really have this two-dimensional system. And now there's many ways that we can find challenges, right? We could consider models with lots and lots of data, but very, very simple models, right? This is kind of your Google scale, terabytes and exabytes of data that you're assuming come from one process over and over again. But you could also imagine scaling up to very, very complex models with very, very little data, right? Or even worse, you can imagine some kind of model whose complexity has to grow with the size of the data, right? Those are notoriously common in these really, really difficult problems. And so if we want to target what kind of tools we should be building, what kind of challenges are we trying to solve, we need to identify where in this space are we scaling. Now, there's lots of ways we can do this, but there is a really nice decomposition of the space that I think characterizes the main two main approaches that we're seeing these days. And this is the so-called tall data versus wide data regime. Now, tall data lives down here. Tall data analyses are characterized by the data being incredibly informative. It doesn't matter if we have a giant data set or a small data set. There's always enough information so that we can constrain all of our parameters down to really nice neighborhoods. There's none of these really, really complicated features, right? This is awesome. Tall data is a fantastic problem to deal with. On the other side of the problem, we have a much more challenging issue. This is the so-called wide data regime, wide data analyses. And this is the opposite, right? These problems are characterized by never having enough information in the data. Again, it doesn't matter if we have a small data set or a big data set, we just never have enough information. This means all of our parameters are distributed across these very, very nasty surfaces. We have these non-identifiabilities. We just have lots of nasty uncertainty that we need to quantify. And if we don't take that uncertainty into account, we get very, very poor use of this data. And so the question then is, which one of these is most relevant to practice? Right? Are most of the challenges out there in this tall data regime with all the structure that we can take advantage of, or in this wide data regime that are kind of have these bespoke problems to every individual analysis?
Can you give us some examples of wide data?
Yeah, I mean, so the classic kind of computer science perspective would be large P, low n, but really kind of any very complex nonlinear data generating process, right? You can imagine hierarchical models. The complexity has to grow with the data. And so you start pushing into this boundary and going a little bit up towards the wide data side. Really, I mean, I'll make an argument in a second, but almost everything is eventually wide data. Any other questions? Right, okay. So to discriminate between the two, if we have some large data set, right, we want to kind of see where we're going to fall. I mean, let's consider what we would typically do in practice. Right, what's the first thing you do when you get a big data set? You clean it up, you might look at some plots, but then you're going to throw a linear logistic regression down. Right? It's always the first step. And so we always assume that our problem is initially in one of these tall data regimes. Right? And if you're dealing with a problem that hasn't really been tackled quantitatively before, this can be a very, very powerful thing to do. Right? You can learn a lot by doing even a simple analysis. But once you've gotten past that low-hanging fruit and you have to start getting deeper into the data set, well, now you've got to capture a lot more and more of that structure, right? And as you add more and more of these features, slowly but surely, you're going to drift up into the wide data regime, right? Again, I've never seen an IID data set. I've never seen a data set so clean that it can fall into this regime without approximations. Every data set I've seen in medicine, in science, and really a lot of industrial applications is really in here. And so it's really a question of how much of that data do we need to take advantage of. So what I'm interested in is building tools that allow us to tackle this wide data regime. Right? What are the methodologies to capture all this uncertainty? What are the tools we need to allow us to implement those methods in practice? Right? And this is a particularly difficult challenge because of all of these very, very nasty features. Now, when we're talking about quantifying uncertainty, Bayesian inference becomes particularly well suited. Because Bayes gives us this very natural way of incorporating all of our uncertainty into our analysis. In particular, we're going to use a probability distribution to quantify which elements of parameter space are consistent with our measurements and which ones are not. Right? And what this allows us to do is then average over all of parameter space. Right? We don't have to make a point estimate. We can take everything into account. And that's what's going to let us make these very, very robust inferences and hence decisions. Now, the posterior itself is built up in a very straightforward fashion. We have two contributions. The first is the likelihood. This is the generative model of the data. This is where we can capture a lot of this very, very rich structure. Systematic biases, selection effects, right? All this can be encoded in a forward way here. And then we complement it with the prior, right? We have this kind of clean cartoon of Bayesian inference. The prior tells us what we know before the measurement. The likelihood tells us what we've learned from the measurement. The posterior tells us what we know after the measurement, right? Very, very clean process. Now, the prior is especially important in these wide data analyses, right? Because remember, the wide data analyses are characterized by not having enough information. And the prior gives us a mathematically self-consistent way for adding more information. So this is a particularly important thing to keep in mind. The regularization we can very naturally get from the prior is very powerful.
Can I ask you a clarification?
Yeah.
question? When you talk about wide data, are you referring to like number of parameters possibly bigger than n?
Yeah. So basically, these very complex, nonlinear data generating processes, right? Basically, anything that's not a Gaussian. Any questions? OK. Right. So we choose our prior. We model our likelihood. We get our posterior. And then again, the idea is to average over the entire parameter space and just use the posterior to weight everything. So now if there are regions of parameter space that are inconsistent with the data, that's fine. The posterior will weight them down to 0. If there's regions of parameter space that are very consistent, then they get weighted up. But in particular, by averaging over everything, it doesn't matter if we have these very, very funky non-identifiabilities, right? Because we're just going to average over everything. And so this provides us a very, very convenient way of taking into account all of this nasty uncertainty, right? It's just the natural process of doing Bayesian inference. Now, the computational consequence of all of this is that everything in Bayes is computing expectations, right? Everything is averaging over parameter space. And I think just want to point out the nice kind of conceptual simplicity that contrasts to a lot of statistical pedagogy. Right? When you take your first statistics class, you're learning all these tests and procedures and corrections and when to apply them and when not to apply them. It's very, very non-intuitive. But in Bayesian inference, we model a prior, we model a likelihood, we compute expectations. Right? That's all we're doing. Right? If somebody tries to sell you a Bayesian analysis and it's not clear where you're taking expectations, be very, very wary. Yep.
So at some point, are you going to discuss where your priors come from?
No, that's a modeling problem. So I'm not, OK, I'll tell you some of the, we can get into the priors of the analysis I'll present. But what I'm talking about is building up the framework that allows you as a user to choose whatever priors you want. Right? And talking about the choice of priors can, hours. And it depends very specifically on the particular application that you're dealing with. Right? There's no recipe for choosing a prior. Just like there's not a recipe for choosing a likelihood.
That's done in bars. OK.
Well, typically you don't want to code in bars. That can be a little bit dangerous. OK, right, so we want to compute these expectations. Right? So at this point, I've assumed you as a user have modeled your prior, you've modeled your likelihood, and now we're getting into how we actually implement this. Right? You've got the posterior already. So now how do we do these expectations? And unfortunately, this is a real challenge. Because integrals, especially in high dimensions, when we have lots and lots of parameters, are really, really, really hard. Like really, really hard. Right? I can't emphasize enough how hard these things are. And one of the reasons why they're so hard is the fact that we just can't think about high dimensional spaces all that well. So I'm going to try to provide some intuition as to what's happening to hopefully motivate what kind of tools we need to implement these, to at least estimate these expectations. Right? And again, this is really, really important because if we can't calculate these integrals very accurately, it doesn't matter how good our model is. Right? Our entire analysis can be compromised if we cannot get good values for these integrals. OK, so let's think about how we calculate an integral. We've got some high dimensional space. Where in parameter space should we look? Right? Where should we be kind of exploring to try to figure out where we're getting contributions to this integral? This is the interactive part.
Where the mass is on the probability.
Sorry?
Where the mass is on the probability.
You've done this before. Right? Naively, where would we look? Well, but what would motivate the grid, right? In other words, like we want to look where the density is large, right? We're looking at this thing. We're going to iterating over lots of f's, so let's not worry about that. And then what's left? We've got this density, right? Nominally, let's just go to the mode where this thing is really large, and that seems like it's where all the integrals would the contributions to the integral would come from. right? But as this man so presciently noted, this is an incomplete characterization. Because yeah, the density is large in the mode, but there's not a lot of volume there, right? Remember, when we're doing an integral, we're integrating over volumes. And while there's a little bit of volume around the mode, there's lots of volume in the tails. And these two things can compensate. So what typically happens is we get the density falling off as we move away from the mode, right? But the amount of volume that we have to integrate over, grows. And this growth grows with dimensionality, right? This becomes exponentially large as we go into higher and higher dimensions. So we get these two balancing properties. And what ends up happening is the probability mass, the actual parts that contribute to these integrals, are in the middle. They're on a surface that surrounds the mode, right? And this is a very, very ubiquitous phenomenon. And so what ends up happening is that all of the point regions of parameter space that actually matter, that contribute to these integrals, are on these weird surfaces that we have no intuition about, right? It's very, very difficult to go to a density and try to backpropagate where this all of these contributions to the integral are, right? This phenomenon, which we call concentration of measure in probability theory, is really what frustrates our ability to integrate, right? Because we need to somehow find this surface. And just for notation's sake, we call this surface the typical set, right? So the key is to somehow find the typical set. And we could do a grid search, right, as was recommended, right? If we don't know where this is, why don't we just brute force and look everywhere, right? So we just start putting grid points down everywhere in space. Well, this thing's really narrow, right? Unless you have lots and lots of grid points, the surface is just going to snake right through everything. And so the problem with doing something like a naive grid search is that it becomes exponentially computationally challenging, right? As you go into higher and higher dimensions, you need exponentially more resources to be able to find this thing. So if we want to estimate integrals in this wide data regime, we need some better way of exploring and finding the surface, right? That's the key problem. How can we find this thing that we really can't quantify in practice? Well, a very, very natural way of doing this is with what's called the Markov chain. And the idea is to take this random operator tau. So this is kind of a random map. We start at some point q prime, we apply it, it just perturbs us randomly to some new point. But we want to engineer this map to satisfy this invariance property, right? And this is some kind of mathematical pedantry, but what this means, if we have a map that satisfies this property, then this transformation is much more likely to move us towards the typical set than away from it, right? A map that satisfies this property is literally attracted to the typical set. And so if we apply this transition over and over and over again, it doesn't matter where we start. We'll get a series of states, the eponymous Markov chain that we'll be using, that drifts into the typical set. And then once it's there, it starts distributing across it, right? So just in terms of a cartoon, again, we have a cartoon of the typical set. I'm going to start somewhere off screen, because in high dimensions, almost every point is very, very far away from the typical set. But we run the Markov chain, and sure enough, we start drifting in, and then start moving and exploring the surface, right? And if we run the Markov chain long enough, it will always distribute across the entirety of the surface. And once it's done that, now we have an identification of the typical set, right? Now we have an estimate for all the points that matter. And so if we want to estimate the expectation of a function, well, let's just average it over those points, right? And this gives us our Markov chain Monte Carlo estimator. And in fact, we can show that if we run long enough, right, as we run the Markov chain longer and longer, we always converge to the true expectation, right? So long as we can set up this Markov chain to target our posterior distribution, we're always going to be able to estimate these expectations, at least in this limit of infinite resources, right? But what's the problem? We don't have infinite resources. So what's of interest to us in particular is not so much this asymptotic behavior, but what happens in a finite amount of time. And this is a much more challenging problem, because you can imagine having a very, very inefficient Markov chain, right? Imagine your Markov transition just kind of jostled you just a little bit, so you don't move that far. That means you're going to need millions, if not billions, of transitions to move across this giant expansive surface, right? But in these wide data analyses, we have lots of parameters, we have lots of data. Those transitions are expensive. We're going to exhaust our computational resources long before we can move across this whole thing. So what we end up getting in practice is this partial exploration, right? And this is obviously going to bias our estimates. If we want good, accurate estimates, we need to explore everything. So a real key, everything, right? Now, unfortunately, most MCMC algorithms suffer from exactly this problem, right? As an example, I'm going to consider random walk metropolis. This was literally the first MCMC algorithm, and today it's still one of the most popular. Right? And one of the reasons for its popularity is its simplicity. It's just 2 steps, right? You always get a valid Markov chain if you take your initial point and add some random Gaussian noise. I'll show that in a sec. Some random Gaussian noise, and then you accept or reject that proposal based on where you land. If you jump towards the mode to region of higher density, you accept. If you jump away from the mode to region of lower density, you reject. Right? So basically, if you jump towards the inside of the surface, you'll accept. If you jump to the outside of the surface, you'll reject. Right? Now, the problem with this is that in high dimensions, our concept of volume starts getting really weird. In particular, there becomes way more volume on the outside of the surface than on the inside. Right? There's just more directions out here. And so when we add random isotropic noise, is the way we try, kind of think about this nice spherical surface, it's going to end up looking like this. Right? Almost all of our jumps are going to fall on the outside of the surface. That's exactly where they get rejected. So we have to go back to where we started, don't end up going anywhere. The only way to maintain a reasonable acceptance probability is to shrink the size of this perturbation. Right? So now we get something that looks like this, but then we're still not going anywhere. Right? The only way to stay in the typical set is to make these tiny little moves, but if we make those tiny little moves, we can't explore all that efficiently. So no matter how we tune this algorithm, we can't get good exploration that takes really good use of our computational resources in these high-dimensional problems. Right? And this is basically the intuition behind the typical scaling of random walk metropolis. Now, this is kind of just like the computational limitation of MCMC, right? If we had enough resources, we'd always be able to get around this. There's even more devious problems with MCMC that most people just completely ignore. Has anybody ever run a Markov chain and seen this? No? OK, I want to ask who's published with this. This is a bad idea, right? This is a biased Markov chain. What's happening is that there's a pathological region in the typical set. Right? There's some kind of region of high curvature. Kind of imagine like you're on a sidewalk and you've got a little crack in there. Right? You can walk around the sidewalk no problem, but you can't, your Markov chain just can't get into that crack. But there's a lot of probability in that crack. And so if you ignore it, you get really biased estimators.
I don't think it's biased.
Yeah. This is not
in the right distribution. So it may have a long autocorrelation time, but it's not biased.
No, autocorrelation, this isn't geometrically ergodic. You have no central limit theorem. I mean, this is a hierarchical model. OK. Anyways, OK. So we get incomplete exploration. We get biases. Now, remember, the Markov chain has to get the right answer asymptotically. Right? So it has to do something to compensate for this. And this is why it gets stuck. Markov chain is actually really clever. So it's exploring around. It's moving through the typical set. Everything's fine. And eventually, it starts getting close to the surface. And what it does is it gets stuck. Right? And if it stays there, you can kind of see what's happening. It's drawing the expectations down as if it were exploring this region. Right? So that's what it does to try to compensate. Now, eventually, it escapes. And then you start exploring more. And if you average that, right, so what we end up getting are these oscillations, right? Our estimates kind of go up and down and up and down. And if you average that for all times, you get the right answer. But if you have only a finite number of iterations, you cut this off, you throw that balance out of whack. And that's what leads to these biases. So when we're talking about scaling up Markov chain Monte Carlo, we have to have very efficient transitions, very efficient ways of exploring these surfaces. But we also have to be very, very careful that we can either explore these pathological regions better, or at least have some idea that something's wrong. Right? Again, the fidelity of these estimates are almost as important as how fast we can compute them. Now, the key to really doing all of this is trying to get around the random guessing that we had in something like random walk metropolis. In high dimensions, the worst thing you can do is guess and check. Because basically the probability of getting a right answer goes to 0 with the number of dimensions going large. So what we need is some better way of exploring. We need a transition that knows this surface, that somehow can use this geometry So instead of having to make random guesses, it can just glide across the surface, right? And this very rapidly moves away from where we started to these new unexplored regions of the typical set, right? And this gives us much, much better use of our computational resources. The question is, and not only better use of our computational resources, this coherency should be able to get us into those little cracks better, right? At least conceptually. So the challenge is, how do we do this? Right? In particular, how do we do this for a generic problem? Because if we really want Bayesian inference to be useful, then it has to be flexible enough that a user can build whatever model they want. Right? They need to build the model that captures the structure of their particular bespoke data set. And then we need tools that can fit those user-generated models. So we need very, very flexible tools that allow us to explore this kind of very large ensemble of problems. Right? And that's a big challenge. Fortunately, we have a solution in Hamiltonian Monte Carlo. Now, Hamiltonian Monte Carlo is a really rich mathematical algorithm. There's a lot of really fun math in this, but I'm not going to bore you guys with it. I'm going to instead try to provide a very high-level cartoon of how we generate this exploration to hopefully build up some intuition as to why HMC is so useful, but also why it has what are the challenges in implementing it, and what are the additional computational tools we need to really make this a viable approach. Right. OK, now to build up our cartoon, let's go back to an example typical set, just to one a little bit cleaner. And again, remember, what we want to do is avoid random guessing. Right? We don't want to guess as to where we're going. That means we need something to guide us. We need something to tell us where to go. And a very natural way of doing that is with a vector field. Now, all a vector field is the assignment of a direction everywhere in space. But if we're careful and we can somehow design these directions so they point along the typical set, then they tell us exactly where to go. Right? If I'm at some point, I don't have to guess. I can just follow this little arrow. And by construction, it's going to bring me to a new point in the typical set. And then at that point, I just follow the arrow, right? And if we keep following these little arrows, what we call integrating along the vector field, we generate exactly the coherent trajectories that we're after. So these vector fields are going to be a very, very powerful way of constructing this exploration. Not clear how to do it, but at least vector fields are something that we can think about concretely, right? Something we can actually build and manipulate in practice. In particular, there's a very natural vector field that we can always construct. Right? If we specify the posterior distribution as a density function, we can take the gradient of that. Right? So if our PDF is here in green, the gradient of that PDF is going to look something like this. This is a vector field. Now, it's not a particularly useful vector field for our purposes, because, if we integrate along this, we fall away from the typical set and crash into the mode. Right? That's not what we want to do. It's good for optimization, not very good for quantifying our uncertainty by exploring the full typical set. So what we need is some way of transforming this vector field, somehow warping it so that it does point along the directions that we want. And this is where that mathematics comes in. But what's really cool is that mathematics that we need to use, turns out it's the same mathematics that describes classical physics. So for every probabilistic system here, there's an equivalent physical system that can be a lot easier to reason about. So instead of thinking about a mode and a gradient and a typical set, these really abstract things, let's think about something a little bit more concrete. We've got a planet, gravitational field, and now we want to take our little satellite here and put it in orbit. Right? Mathematically equivalent system. In particular, it should suffer from the same pathologies, right? So if we take the satellite and just put it out in space, what's going to happen? It's going to crash into the surface of the planet, right? But from the physical side of things, we have some workarounds, right? How do we get things to stay in orbit? Speed, kinetic energy, motion, right? What we need is transverse momentum to balance against gravity. But we have to be careful in how we do this. If we add too little momentum, well, then gravity still wins, right? We delay the inevitable a little bit, we still crash into the planet. If we add too much momentum, well, then we fly off to infinity, right? There's not enough gravity to capture us at all. But if we're careful, and we add just the right amount of momentum, well, then the equations of motion that describe the system are exactly the vector field that we want. And then the corresponding physical evolution gives us exactly the trajectories that we want. So the key to taking something like the gradient of the PDF of our posterior density and transforming it so that it points along the typical set is to add these momentum parameters in just the right way. And that is exactly what Hamiltonian Monte Carlo does, right? This is the key. Hamiltonian Monte Carlo is a somewhat unique procedure for adding these latent parameters to give us this, to take the gradient to warp it so that it points along the typical set. So I'm just going to go a little bit more in depth into how that works, just to give some things to some names to things, just because I want to emphasize some of the challenges with doing this in practice, right? Sounds really good. There's some subtleties. Now, to do this a little bit more explicitly, we're going to add a momentum parameter for every parameter in original space, right? So we're going to double our system. And then we're going to have to lift up our probability system. So we're going to start with the posterior distribution on Q. We need to define some kind of probability distribution on P and Q. Right? Now we're going to do that by choosing a conditional distribution for the momentum. Right? So we have our posterior originally, and then we're going to add this conditional distribution. And this is important because what it allows us to do is throw the momenta away. We can always just throw everything away, go back to where we started, and we always recover our original system. So what happens graphically is we start with our target distribution. We have our posterior on our original parameter space. We lift up onto this extended system. Right, so we get this bigger probability distribution. And then it turns out this space has a very, very special property that allows us to automatically construct the vector field and then integrate to get these trajectories that we want. Right, this is where, again, where the math comes in. Right, so what this kind of procedure allows us to do is automatically generate these trajectories that we wanted. Right, this was the key to getting more efficient use of our computational resources. Moreover, not only are these trajectories more efficient at exploring the typical set, they're also better, at dealing with these pathologies. Because what happens is these trajectories are able to get into those cracks a little bit better. Now, it's not perfect, right? It fits more of the problems out there, but it still has pathologies it can't deal with. But this is the really, really important thing. When Hamiltonian Monte Carlo encounters one of these neighborhoods, it goes crazy. Right? Imagine something like a random walk metropolis or a Gibbs sampler. It just kind of bounces over this. It just completely ignores it. And unless you run your chain long enough to see you get stuck, you have no idea it's there. But when HMC hits one of these things, it bounces off, flies off to infinity in a very, very violent process. So we can actually capture this. HMC is not only faster, it's not only more efficient, it's not only better at trying to tackle these problems. When it fails, it tells us. And that is an incredibly unique property for these computational problems. Yep.
So when you say it bounces off
Yep.
to infinity, you also imply that it doesn't have the property of returning to the set.
Yeah.
So you need to know in advance what the typical set is?
No.
Nothing there?
No, so literally what happens is the symplectic integrator diverges.
What? Say again?
The numerical approximation of these trajectories diverges. We capture that as a NaN, and that gives us a clear indication that something's wrong.
And then what do you do?
I would report it to the user and say something's wrong. So this gets to the kind of point where there's no automatic way of fixing this, right? There's no like immediate fix. This is a user problem where we need to start talking about, parameterization might be tricky. Maybe you want to simplify your problem a little bit. Maybe the data's not quite right. Maybe you need better priors, right? There's a kind of ambiguous way of solving this. So we have lots of methodologies built up around this. But what's really important is step one, just to know that something's wrong.
Well, why is it the user's fault?
Because the user specified their model, right? We're in this process where we want the user to be able to specify whatever model they want.
Yeah, but what does it mean to have a wrong model?
It's not, the model's not wrong, right? It's just their tools are not able to explore it.
But just to be clear, I think that random walk metropolis doesn't have this issue.
Random walk metropolis is not geometrically ergodic on these kinds of models. It doesn't satisfy a central limit theorem.
Oh, okay. We have to.
In a standard parameterization, a hierarchical model is not geometrically ergodic with respect to a random walk sampler. I mean, that's a known result. I can bring out the papers.
Well, it depends on the distribution.
Yeah, I'm saying a hierarchical model with a standard probability distribution that has a hierarchical structure as a very, very typical pathology that frustrates geometric ergodicity.
Do you have a specific example of a hierarchical model? It's a very simple example that you can take us through later and also point out this issue and how you expect the user to fix it?
I can do it on the board. I don't have slides prepared for that. But I mean, you can imagine, so like an 8 schools model, right? The classic, do you know the 8 schools model?
No.
Okay. Do you have a favorite? Okay.
Educational data is hierarchical.
I understand what hierarchical models are. I want to understand specific example of where we see this phenomena and why the user is supposed to fix it.
So what I mean, okay. Let me go back to this picture. Right, this is the basic pathology that you get, right? This means that our Markov chain is not able to provide accurate estimates of the expectations, right? If we had a better sorry? And finite number of steps, yes. I mean, so in practice, we can't do it, right? If we had a better tool, maybe we could get around this, right? But as a tool provider, this is the best we have, right? Whether we're talking about running something like bugs and JAGs.
Are you looking at a single random variable? That's y-axis?
Yeah, this is one particular random variable, right? Particular one that captures the hierarchical structure quite strongly.
Why does this illustrate a problem? If you run this a little bit longer, it could be there.
No, this is the kind of thing that like in no finite time will this converge to the right answer. I mean, I can talk about the mathematical details with you later, but I can promise you for finite time these things are horrendously.
What does the right answer mean for you?
It means getting the expectation within some known variance. These can be horrendously biased estimators of the population level parameters.
And what's the picture that you would expect to have? Basically, if you saw this behavior over and over again, zoomed out long enough, it could be that the chain is mixed and that the mean is 1/2 or something like that.
You wouldn't get this kind of mixing. This would either be bimodal, which is another problem.
Why is that a problem?
Because it's difficult.
Here it could be bimodal.
Look, if you have a sampler that can solve all of these problems, I'd be happy to take it, but we don't. Right? This is the challenge. The user can provide whatever model they want, but it's no guarantee that we can compute expectations with respect to that model in a computationally efficient manner. Right? This is the challenge with computational statistics. We want to build tools that allow users to build as flexible of models as possible. And because we can't fit everything, the best we can do is be able to report when we can't do that. And that's something that most tools don't have. So it's a really, really novel contribution. Again, we can chat later. But I think the ideal of solving everything is not something.
Solve everything.
What's that? OK. Well, I'll be waiting for your Nobel Prize. OK, so where were we? Right. OK, so again, we have these self-diagnostics that are incredibly important. This is some of the recent work that we've been doing. Right? So again, we report it to users. If it doesn't fit, then they have something that they can use to acknowledge their problem. OK. Now, just to get a little more nomenclature of what's going on. Again, we have this distribution on our larger space. We have our posterior distribution and this conditional distribution for the momenta. It turns out that minus log of this density, is what we call a Hamiltonian function, hence the name Hamiltonian Monte Carlo. This is what generates all of our motion. Right? So this is the important thing that matters. And this is formed of two components. We have this component here, the minus log of our conditional distribution. So we call it kinetic energy. This is just using that physics analogy for some naming. And then we have this minus log of the posterior distribution. Right? So we call it potential energy. Right? So our motion is going to be built up of these two terms. Now, the important thing here is that this potential energy is completely specified by your problem. Right? If a user comes to me and says, here's the posterior I want to fit, I know what the potential energy is. What I don't know is what this kinetic energy is. That is a free parameter in this model. Right? But for any choice of that parameter, we're going to get this kind of coherent exploration. In particular, we always get this kind of vector field. You can see we get an arrow in the parameter direction, and we get an arrow in the momentum direction. Right? And the thing to notice here is look at dV/dq. Remember, V is the posterior density. dV/dq is that gradient that we were using before. Right? And just as I argued in the cartoon, all we're doing is taking the gradient and adding these terms that warp it so that it points along the typical set. Right?
So just a general question.
Yeah.
The kind of like white data.
Yeah.
Oftentimes we have a lot of parameters and very few data.
Mm-hmm.
So the actual, you can do whatever. The kind of density surface is going to be really
Yeah.
very sparse.
Right. That's why we want to be able to integrate over all of it.
Right. But, okay.
So I mean, you can get all kinds of complex structures, and what will end up happening is the trajectories will get really, really kind of these tiny little oscillations that move through.
Imagine you get a lot of like singularity.
Yeah. So we have to be careful. But those singularities we get reports on.
But would there be like too many? So that
They could be. Right? There could be problems that we just can't, we can't get into those cracks. right? And that's something that we'll push the tools and hopefully be able to do better at. But again, the kind of big hope that we can try to produce is fit as many problems as possible, and then when we don't fit, report that we haven't done that, right? And that's something that I'll claim very strongly is something new. Okay, right, now this, when we start talking about implementation, we have to start dealing with some unfortunate things. In particular, we can't actually move along these vector fields analytically. We've got these little arrows in space, and we just don't quite know how to move along them in a general fashion. So what we're going to appeal to is a numerical approximation. Right? We have to numerically solve this system. And it's usually straightforward. There's some nice, kind of time discretized things that look, like they might solve it. But there's a challenge here in that this always introduces some error. Right? Our numerical approximations are always never quite exact. And that will bias the Markov chain in really complicated ways. But fortunately, there's a pretty straightforward solution to that, and that's where we add this acceptance probability. And so the idea is basically doing something similar we did with random walk metropolis, right? Treat these numerical trajectories as a proposal, right? So they're moving along. We kind of decide we want to look at a point. If they're close to the true solution, we'll accept them. If they're far from the true solution, we'll reject them.
What is 5 tau?
This is just the density on the joint space. Oh, so there's an extra correction that goes in. Sorry, okay, so P of Q is our momentum and parameters. Phi of tau is the numerical solver going forward. So this is the final point.
Proposed move.
The proposed move, yeah. And then pi is the density that we saw before, sorry. And then there is technically one other complication here, but more or less this is what we got. Okay, so when we put all this together, right, we have to do this little subtle correction, but this is like 10 lines of code, maybe 20 if you want to be fancy. So you can go to your favorite programming language, spin this thing up, and nominally you're ready to run HMC. Unfortunately, very soon you'll realize there's something missing. Right? It's very easy to write this down as code, not so quite easy to build in all of these inputs to the code. Right? In particular, we've got to compute derivatives, right, to get the gradient. That's taking this density function, which could be hundreds, if not thousands, if not hundreds of thousands of dimensions, and getting all the gradients out. And I can attest from personal experience, this is what I did in my thesis, not fun. It's a very, very time-consuming process, and it's very, very error-prone. Right? That's just not a good sign for a robust algorithm. And even if you can do that, what do we choose? How do we choose this kinetic energy? Right? There's this free parameter here, and as I said, every choice of kinetic energy does give coherent exploration, but not all of it is going to be as effective as others. Right? You can imagine having these nice straight trajectories. You'd also imagine having trajectories that oscillate back and forth. Right? Those latter ones aren't going to quite be as efficient. They can be much more wasteful of our resources. And so there's a lot of care that has to be done in choosing this T. And then there's the integration time. Right? How long do we actually move along these vector fields? Obviously, if we don't integrate that long, we're not really leveraging this exploration. But it turns out you can also integrate too long. Right? You can go too far, and that's also wasteful. So there's a delicate problem in how we choose this. And then there's the numerical discretization itself. Right? There's a lot of tricks in trying to make sure this is accurate enough to capture our system. Yeah.
So what happens when you go too far? It means the integration fails? Or?
Oh, you'll reject, right? So you get lots of errors that build up.
You go too far because essentially you're losing precision. As you
Yeah. So you have to be careful to have enough precision to, and it's a little bit more complicated. We have symplectic integrators that have kind of a different precision issue, but that's basically the issue, right? How do we tune the numerical approximation to get the best performance?
What is tau?
Tau is the integration time. So it's how long we move along the vector field. It parameterizes those trajectories.
What's epsilon?
Epsilon is the numerical discretization of the trajectory itself. So think ODE. Time is the amount of time we integrate the ODE, or tau is the amount of time we integrate the ODE. Epsilon is the discretization of whatever numerical ODE solver we use. More or less. Again, there's a lot more details here. I'm trying to provide high level. Okay. So what ends up happening is that if you try to run HMC naively and don't know how to tune all these parameters, you can get really, really terrible performance. Right? It's easy to walk away and think that all this complication isn't worth it. But if you have the time, if you have expertise, or if you can empirically test all these inputs, you can get drastically better improvement. Right? Many, many orders of magnitude. And so the challenge with something like Hamiltonian Monte Carlo is trying to realize that theoretical potential into something practical. right? And this is where all the math comes in. Right, so a lot of my research is focused on building a mathematical framework that we can describe and understand this algorithm. And what that allows us to do is understand mathematically how these inputs affect performance. So we can build up optimality criteria, and those optimality criteria can lead to automated algorithms. Right? If we understand how the inputs affect the performance, we can tune to it automatically. Right? And these kind of understandings are really, really critical to tools like STAN. Because what we're able to do is automate the application of Hamiltonian Monte Carlo. And this allows us to decouple the modeling from the computation. So in particular, STAN is a computational library. You can run it in R, Python, Stata, whatever language you like. And what we do is we expose 3 basic components. We have a modeling language. This is a language that allows you to build up these big complex models. So as a user, this is like a vocabulary for specifying the model that captures the bespoke structure in your data. Right? Again, the flexibility to build up that. Then we have tools like automatic differentiation, which allow us to automatically get those gradients. So once you specified the model, you're done. We compute the gradients, and then we use all this mathematical understanding to build up these adaptation algorithms. So we run HMC automatically. So you provide the model, we take care of everything else. And at the end, you get your estimates, and you get these diagnostics that you can then use to build confidence. Those estimates are accurate. Now, one of the great joys of working on STAN is seeing the user community that's developed around it. Right? STAN's only a few years old, but we have this incredibly innovative community that's taken it and used it up to build these novel analyses and a really wide diversity of fields. Right? Everything from medicine to industry to science, it's just all over. It's really, really cool to see what they can do. And I just want to provide some examples that I think highlight some of this work. So this is work that I've personally been involved with, where STAN has been critical, right? All of these tools, having Bayesian inference, having things like Hamiltonian Monte Carlo, it's really enabling us to take active use of the data set that we're collecting. And the first one is epidemiological, right? This is the example I mentioned before with malaria. Right, so remember, we had this very complex data set. We had this whole population of mice. We had this propagation of malaria through the mosquitoes. But we had all this data, right? And now we want to build a model that can capture all that structure to allow us to make these very, very informed decisions as to how we should be deploying these vaccines. So I'm just going to go through the basic model components and some of the STAN code. The first is the initial mouse population. Again, there's that natural variability, just because some mice get more infected than others. So we modeled that with a hierarchical model. So we have some random effects on there to account for that variability. The individual measurements of these densities went with a zero inflated negative binomial. We started with simple binomials. We tried a Poisson, and the model was just too nasty. We've got a lot of complex effects going on. So we ended up going to a negative binomial distribution to get more flexibility. But then we saw something weird going on. Right? There was all of these excess counts at 0. What was happening is our treatments were too good. We had a lot of uninfected individuals that were propagating through. So we had to add the 0 component to take that into account. Right? But again, STAN allowed us to do this no problem. Right? We just kept building the model we wanted to, and at no point were we really limited. And then the actual transmissions we approximated with the general linear model. So we have this really nasty convolution process between these distributions, and we just linearize the negative binomial parameters and just map them forward in a straightforward fashion. So in terms of the STAN code, it's all pretty straightforward. I mean, there's some complexity here, but this was to make it general. So you can see that for the negative binomial parameters, we get kind of our mean effects, and then you get all of these random effects that are specific to every individual. So every mouse, kind of in every group and every treatment configuration, is able to get these special effects. This allows us to model that variability in a coherent way. And just a few lines of STAN code. The density of the cells are modeled with the zero inflated negative binomial. This looks a little clunky, but I want to emphasize how many codes out there have a zero inflated negative binomial built in. I mean, STAN doesn't. But what's important about STAN is that we can do the zero inflation ourselves. Right? We have the flexibility so that we can get around the limitations of what are the default distributions provided. Right? We can build in what we need to.
So that's user provided? This is all the...
Yeah, so this is the model that the user would provide. Right? And the whole thing is something like 200, 300 lines. I'm more happy to show it to you afterwards. Right, so again, we're able to do zero inflation. The spore density is a really cool one. So due to some computation or experimental limitations, the spore density data was not point density data. It was actually interval data. It had to be censored. right? So instead of getting that, there were 10 spores per, liter of blood, what we had were, there was somewhere between 10 and 100, somewhere between 100 and 1,000, right? This is the kind of thing you see in real data. You have these censoring effects, and there's no way to get around it. So you model it. And what that needs, in order to do that, you need these negative binomial CDFs and build up a multinomial distribution. Straightforward process. Not a lot of packages support it. But in Stan, right there, right? Again, it's the flexibility of the language that allows us to build up the models to the data and not to the limitations of the language, right? Now, this isn't, I should note that these distributions here, I had initially coded in, were not great. And to get this thing working required about 10 pages of algebra to get a better computational implementation of that, right? That's the work we do. You find problems, we'll help build them up. Try to make this as ideal as possible. And then the general linear model, again, it's just a linear model, right? Just a Bayes-Tree matrix multiplication through.
So that means that the next person who's dealing with the
Yes.
same problem, they won't have to
Nope.
won't have to be resolved.
No.
Just sitting there.
Yeah. Right, basically what we're trying to do with the user community, and I'll talk about this a little bit later, is find all the problems with Stan. Right? Having these large user community, having us build these analyses, we're pushing all of the buttons. When we find problems, we fix them as soon as we can. And this was a particularly nasty one, but we eventually got it. And I was really happy because you'll see these results were phenomenal. So again, because we built up the model that captured the data that we wanted, right? Because we actually got that structure, we got these incredible fits. These are just some of the many posterior predictive checks that we did. And you can see we have really, really nice agreement between the censored data that was both predicted by the model and what we fit. And this is really, really important because this now gives us confidence that this model that we've made, the assumptions that we've made, the priors, the likelihood, is really capturing the structure that's there. And this then gives us confidence.
Wait, can you go back to that?
Yeah.
Because I'm way too blind to do
Oh, are we, I mean, so I'm not, and this is not meant to see, kind of the qualitative results. I mean, you can go through and you can kind of see they're all within the 95% quantiles of the predictive distributions, et cetera, within the multiple counting effects and all of that, right? But it's quite good.
How many data points do you have where the prior is actually affected?
Oh, well, in this case, lots. That's because there were some tricky regularization issues. But this is also a case where we have lots of scientific information to guide those approaches of priors. Right? Basically, we know the units. We know the typical variations of these kinds of problems because we know the physiology of the mice, we know the physiology of the mosquitoes.
Right, but usually if your data points, if your N is large enough, your prior just kind of doesn't.
Not necessarily. That's only if your likelihood is sufficiently simple. Right? Bernstein von Mises only holds up to very, very strong regularity conditions. Well, people would argue they're relatively soft regularity conditions, but you have to have your likelihood going Gaussian, and then oftentimes the priors don't matter. Again, subject to some regularity conditions. But this is a model where those things wouldn't hold.
I have a question about data. So you're trying to figure out your random effects with now.
Yeah.
Are you actually being able to keep track, like how many times a particular mouse being
Oh, yeah. So that's actually done. Yeah. So all of that stuff is done in the experimental setup. And so I didn't have time to get into it. But you can actually count the number of times the mosquitoes bite the mice. And that's one of the random effects. We have multiple.
one mosquito?
No, so we have 500 mosquitoes. They're starved. And then they're allowed to bite the mice a certain number of times. So there's 2 bites, 4 bites, 6 bites, 8 bites, 10 bites. They can actually capture that to ensure, because when they get bitten, there's this giant welt. So
Trying to think of how this data is possible.
yeah, no, it's really, really cool data. I mean, you can see the whole setup, but it's very much grad students spending many, many weeks of their lives just looking at mosquitoes biting things. It's just a huge effort that they've done. I cannot congratulate them enough. And it turns out it's really clean data. It actually does capture some of this stuff. Although I'll say, the first data set that we had was that they had a really weird effect. When they were fitting the model, there was this weird discrepancy. And it turns out there was an error that one of the students had done. And we were able to go back and correct that, and we resolved errors, right? So again, having this model to capture those things, we can actually find these problems, if not model them explicitly. Yeah.
Just a point of question. Can you explain what the model diagnostics are? Like how you know, you said you went through like choosing, you ended up at the zero-plated negative binary.
Right.
How do you know that the other choices were?
So this was basically the kind of more qualitative posterior predictive methodology. So we would look at predictive distributions, we would look for deviations, we're just seeing if we're capturing the distributions. And that one was pretty easy to see.
It's like residual analysis.
Yeah, basically fancy residual analysis. Yeah. What else? Okay. Oops, let me go back. So we were, right. So now that we're confident with the model, we're in this position to make some really, really cool efficacy recommendations. And this is something that we're particularly excited about. Because typically in epidemiology, you just look at the initial parasite density and the final parasite density, and you just see, did it go lower, did it go higher? Right? Sometimes you don't even get that. Sometimes you just see if there's less cases or more cases. And that's a very, very crude way to try to recommend how we should be treating individuals. But because we have data through this whole process at every one of these stages, now we can start making very sophisticated definitions of efficacy and recommendations, right? We can start saying, well, maybe vaccine A is better if we can only treat once. Vaccine C might be better if we can treat in stages. Vaccine D might be better if we can only treat some subpopulations, right? These are the kind of things we can start now moving into. And we're really excited about what the kind of contributions we can make to epidemiology just because we have the model to really leverage this information from the data. Right, so some really, really exciting stuff there. And then secondly, I'll just mention this analysis that I did with a colleague who was at the time at Harvard. I like this one because of the time constraint. This was a grad student who was finishing up his thesis. He had a few months left, I think about 2 months. So look, I'm defending my thesis on this day. I'm not a huge fan of my model. Can we do this better in STAN? And I was like, all right, let's give it a shot. And in 2 months, we had a complete model built, about 10,000 parameters, fit in STAN, beautiful, beautiful results. Right? And I think it just demonstrates the power of what you can do when you're able to decouple the modeling from the computation, at least as much as possible. Now, this particular analysis was looking at supernova. These are these exploding stars in the sky. Very, very pretty to look at. There's this very rapid explosion, this kind of slow decay, this plateau, and the slow dimming down. Right? So you have these very, very long explosions. And the better you can measure this, of course, the better you can understand what caused the star to explode. But turns out, if you can measure lots of these supernova, you can use them as guideposts to really constrain the structure of the universe itself. Right? Very, very powerful for cosmology. Right? The kind of basic questions of how old is the universe? Right? How big is the universe? The challenge with these is that they're rare. Right? They don't happen all the time. And so if we want to get a big enough sample to start answering these very deep cosmological questions well, we need lots of supernova. How do we do that? Well, this is why we're doing a lot of surveys in astronomy these days. You take a telescope and you scan it through the sky over and over and over and over again, right? Kind of making a movie. And the idea is you have this, exabytes of data, and there'll be enough supernova candidates in there, right? And indeed, that's true. But what's going to happen? Remember, you're scanning across the sky. So you're much more likely to just clip a supernova, just get the end, than you are to get the beginning. Right? So you might get the dimming, you might get the initial rise time. Turns out it's very unlikely to get a complete, beautiful, unbiased observation of a supernova. Right? And so this is exactly the same circumstances we had before. We've got this large data set, but it's structured, it's nasty, it has these biases. And if we don't model them, we're really limited in what we're able to extract out. So this analysis, I'm going to show you the STAN code. It's a lot longer. This is kind of the hierarchical structure. You can see we had many, many hierarchical components over the supernova and over the systematic effects and the wavelengths, as well as the kind of deeper hierarchies to take into account some richer structure. Ended up about 10,000 parameters, threw it on STAN on a cluster, day and a half, 2 days later, we got our results back. And they were really, really cool. This is just a comparison of the individual model. This is the simpler model that didn't capture all the structure into account. And you can see it fits OK where there's data, but it does really poorly on this unobserved region. Right? Not this is poorly, it's just a lot of uncertainty. But our model, because we captured all that systematic structure, because we were able to model the biasing procedure, we were able to get much, much smaller uncertainties. And in fact, you can see there's a strong shift. Right? We're not just getting more accurate answers. We're not just getting more precise inferences. We're getting more accurate inferences. And this is a big deal, because these surveys are incredibly expensive. Right? We're talking about hundreds of millions of dollars in terms of observation time. I have a colleague who's doing something with 1 million parameters, really looking at the evolution of the universe. And using STAN, using HMC, he was able to get 10 times better signal to noise, which corresponds to 100 times more data. Right? So if each of those data sets are hundreds of millions of dollars, imagine what it's like to get 100 times that for free just by using better analysis techniques. Right? This is really, really important when we have very expensive data. So I'll kind of end there. We're not anywhere near done. Right? As I mentioned, we know there's limitations of HMC. We know there's limitations in STAN. But what's really exciting is that we have this user community that's helping us find them. And so what we end up getting is this really powerful feedback cycle. Right? We're pushing the limits of data science as much as we can. By providing these tools to users, they can come in, build those analyses, populate those frontiers, and then identify where we need to go next. And so we get this really, really awesome cycle where we're not just doing better statistics, we're not just doing better theory, we're really enabling analyses. And that's what we're really after. Thanks.
I'm a user.
Yes.
And I just started using that.
Ooh.
But my problem is I'm a Windows user.
Well, so this goes beyond a little bit the scope of the talk. I mean, this is a serious issue. So a lot of our users are Windows users. And so two of the stand devs are out in the back, and I think they can attest, we spend a lot of time not doing statistics and a lot of time supporting Windows. And we wish it wasn't that way, but this is one of the challenges. When you're doing real world code, it's not the fun things you really want to be working on, it's these nasty issues. So what in particular was your issue?
It just doesn't work reliable. It was a simple model.
Which interface?
I'll use R as
Okay, so you're using rstan,
RSAN, yeah.
and you installing through CRAN?
Huh?
Installing through CRAN?
I'm sorry, what did
You're installing through CRAN?
Yeah.
Okay, well, we can talk about,
But
yeah.
it was just
Yeah, no, Windows is,
you're set and stand right.
yeah, no, hey, I would almost rather buy you a new computer than have to deal with the Windows, but we'll make it happen. Any other questions?
So the Bayesians are all hot on stochastic variational inference.
Yes,
Right?
with
And
some of the
The
Bayesians.
hype is that it's going to change the world and no one needs MCMC anymore or
Yeah.
HMC.
Yeah.
What do you say to that?
Well, funny you should say that. Sorry, I don't actually have slides for this. So we have a we have a variational inference algorithm in Stan, right? So we're working with Dave Bly and Alpa Kukub. I can never get his last name right. Big long Turkish name. And they've taken their black box VB algorithm. So VB has a few issues. One of the issues is that it's very difficult to generalize. You have to kind of build it up specific to an analysis. And that makes it very difficult to apply to these general models that we want users to build. So Dave and Alp and a few others developed this kind of general tool that nominally should work. It should be able to hit that using gradients and all the tools we already have in Stan. So they put it in Stan. It's something that we've been playing with. But one of the things that we've seen is that even on relatively simple models, it gets really, really biased answers. Right? And some of that is understood. Right? We know there's limitations to VB. And so this is a computational challenge. Like, what is the trade-off between accuracy and speed? And one of the really nice things about MCMC is that we can quantify that really well, right? We really can, subject to certain regularity conditions, which hopefully we'll be able to quantify with our diagnostics. We know what our accuracy is, and we can kind of get an idea of what the trade-off is. But with VB, that's a big open world right now. We don't really know the models it's going to fit well on and where it's really going to fail. So I think there's a lot of potential for VB, but it's not yet. A lot of work needs to be done. A lot of statistical work, a lot of theory needs to be coming to support that. Because right now, every time we run it on a suite of models, it's mixed results. And this is relatively simple stuff. So it's a, open game. Depends what your uses are. A lot of people who are using VB just want quick answers on giant data sets. That's fine. VB can work really well in there. I want really accurate answers to allow us to make really good decisions. VB is not going to cut it yet.
I work in computational neuroscience. Some of the models that we have are not really analytical. So we do say we need to do numerical integration.
Yep.
It's very complicated. So we'll stand support this and be able to perform.
Yeah, so it depends. So for example, we have ODE support in Stan. So you can build your model up as just the implicit ODE. We'll integrate it. We'll get the derivatives through the integrator and do all of that behind the scenes automatically. And we just recently have CVOD in. So we now should have state-of-the-art nonlinear solving. So if you can build up your model that way and specify it as an ODE, then yes, Stan would be totally applicable. If you have some custom numerical library, probably not going to happen. But that's all due to the derivatives. So and again, there's potential, but probably not immediately. Yeah.
You mentioned at the end that Stan still has some limitations.
Yeah.
I'm curious about what types of problems it.
Yeah, so there's always going to be scaling limitations, right? Like as we go to more and more dimensions, we get more and more of this concentration of measure, and we have to, the kind of more singular part of parameter space to look at. And then we get numerical issues because we have these approximations to the trajectories, and they don't always, quite get what we want them to. And so it gets slower. There's tuning issues. As we go to higher dimensions, tuning these input parameters, the kinetic energy, the integration time become really important. And we have decent results, but we'd like better heuristics for that. There's, as we push to more and more complex models, we see different pathologies. So we're trying to, take our fits and feed it back into a lot of theoretical work that we're doing to better understand, what kind of things to be looking out for. New diagnostics report to users, that's something that potentially be off. As well as just new components of the language, right? Like adding more distributions, adding new numerical features, and trying to rush to kind of satisfy the users who are demanding things and make this as expansive as possible. So it's just a huge amount of little things like that to do. The biggest limitation that people throw out are discrete parameters, which we can't do because there's not really an HMC equivalent for discrete parameters. This is another tricky issue. You can throw out a discrete sampler, but it's really difficult to quantify the potential errors with those. We do a lot of tricks with marginalization to get around that, but there's some models that are still tricky to do because of that. Things like point processes, so some other particularly common models. Non-parametrics are tricky. There's some tricks to do, but that's not something that's quite applicable yet. I don't know, have I missed anything?
Well, the Gaussian processes are pretty slow, but we're working on that.
Right, but I also think that's partly a modeling issue. Those hyperparameter posteriors are nasty. That's something, another thing. So one of the interesting things about Stan is that sometimes we'll get to a new problem and we'll try to do the full fit, and we'll just realize there's problems that people haven't seen yet because they're doing point estimates or they're doing these simple approximations. And GPs are one of them. The kind of non-identifiabilities you get with GPs, which makes sense theoretically, but you really see it in practice, and it's a big limitation. So it's a really nice kind of research tool as well to start identifying the problems and maybe potentially finding workarounds. So we'll see how that goes.
I think in the past few years, Stan's been really successful in just becoming sort of off the shelf, right out of the box apps. And I think that's reflected in the number of domains that are used.
Yeah.
I just wonder, first of all, is that sort of the goal that you're working towards? Second of all, if so, are there some sort of are there larger consequences that might have in terms of just how people approach the Bayesian inference process?
Oh, I would hope so. I mean, I think I can speak for myself. I think it's a similar story with these guys that we just had problems that we couldn't solve. And we wanted to do them in a Bayesian fashion, but the tools really weren't there. And things like bugs was revolutionary at its time, but it's hit its limits of what it can do. So we're hoping to provide that next step, the next evolution of those kinds of tools to exactly, make Bayes easy to do and allow people to focus on the models they want in whatever domain they're at. And it's really fun. We'll go to, last year I was going into a bunch of pharma conferences. Pharmacology is big, complicated models. And some people had heard about Stan and wanted to play with it. It wasn't quite perfect yet, so we built the ODE solver, right? And so it's this constant feedback of wanting to help people solve problems, going to the domain, seeing what they need, and trying to support that, and then expanding and propagating. And then we solve the ODEs, now we go to ecology, now we go to physics. It's a really cool kind of synergistic effect. So I think ideally we like to solve as many problems as possible, and just make science easy, or easier than it currently is.
Can I say something here too? I think among the people working on the project, we have very different goals. Like Michael does almost all of our theory, right? And I do most of the core language stuff. Daniel does most of the core engineering. I want to make this available as a tool, but there's also a lot of theoretical insight that I think we're looking for here.
Yeah.
Just in the general way that you can do Bayesian statistics.
Yeah, I mean, it's a platform for research, right? And it's been tremendously successful. I think it'll be tremendously successful in the future. So it's not clear necessarily where we'll be in 5 years, but hopefully somewhere good.
You mentioned diagnostics.
Yeah.
Does the algorithm give you any new diagnostics over any standard, MCMC?
Yeah, so those divergences I mentioned? Yeah, so that's the really key one. There's a few others that I'm experimenting with that are kind of being motivated recently by some theoretical work that I've been doing. That'll be a little bit trickier to understand, but might still be useful. But the really big one are these, these trajectories just flying off to infinity.
Yeah, okay, but I was actually thinking more where you're pushed a little bit away off the path.
Yeah.
But you're not flying along.
But so we can quantify those errors. So if you're just a little bit off, because you're always going to correct for that, the answer is still right. It just might not be quite as computationally efficient as you want. So those kinds of issues where you're just kind of oscillating a little bit too far, That's not so much an accuracy issue, that's an efficiency issue. And something we like to solve, but not quite in the need of a diagnostic. Does that make sense?
Yeah, I'm looking for, again, ways of sort of seeing where the model can improve.
Oh, so improving the model is a different question, right?
No, it's going to be a function of what you're looking at in the data.
No, sure. But the thing with, again, with Bayes, any kind of model validation is going to be an expectation. And so if you want to have a robust way of doing posterior predictive checks, doing any kind of residual analysis, we need to trust your expectations. And so the hope is that by, again, if we can decouple all of this and HMC can provide good answers or identify when it's not providing good answers, then you can, as a user, can focus on developing these posterior predictive methodologies. And that's something that we also work on. Andy and I and a few others are really, and I think you guys too, are interested in like, how do we do posterior predictive checks? How do we do predictive validation in a very generation way? And Stan has allowed us to experiment and really expand what we can do with that.
That was the focus of our latest grant proposal.
Yeah, yeah.
We'll see whether we have funding to hire somebody more.
Another question.
Yeah.
So this is back to Hamiltonian Monte Carlo
Yeah.
in general. So I was wondering, so suppose that for a model is it's hard to do derivatives or
Yeah.
it's not feasible, or let's say, would you still recommend, say analytically,
Yeah.
would you still recommend to compute numerical derivatives and still use Hamiltonian Monte Carlo as opposed to other ways of sampling?
Is really tricky. So remember, autodiff is not quite the same kind of numerical derivative as most people think. It's not finite differences. So there's there's really no compromise for doing that. If you can't use autodiff and you don't know how to do analytic derivatives, so you're limited to something like finite differences, if you're guaranteed that everything's smooth and it's just a question of calculating it, it could be better than nothing, right? Because HMC can be so much more efficient than other tools, even doing an approximate derivative can be helpful, but in high dimensions, it's a really delicate game, and I've yet to see many examples where doing an approximate derivative was helpful, because you just fly off so quickly. This is a big issue with things like stochastic HMC, trying to use emulators, the Gaussian processes. Just high dimensions are really hard, and they really frustrate these kinds of ideas.
What do you define as high dimension? Because you're spoken about 1 million.
Oh, yeah, anything from, basically, like at 100 dimensions, things start kicking in really hard. And then you go up to thousands and millions, they get really bad. So the problem is, like, there's not an absolute answer for any of this. It's all these like soft depends on this, depends on this, depends on this, depends on this. But it's worth trying, and you can kind of quantify what's going on using the diagnostics. And we'd be happy to chat about it either a little bit later or on the Stan users list.
So just I want to hear your opinion. So what's happening in, let's say, neural net community
Yeah.
is that the people are actually working on the things that are supported by, let's say, piano,
Yeah.
TensorFlow,
Yeah.
right?
Right.
So rather than they're trying a new thing and then add it to the piano,
Right.
for instance, it's often becoming like the other way around.
Yeah, yeah.
So do you see any kind of, let's say, that trend here in the Bayesian community as well? Let's say, like, whatever is supported it works on Stan, where I'm going to do it, but if it's not, then you're like, okay, maybe it's not the easiest thing to do. Okay, I'm going to try something else.
Right.
that is supported by Stan.
No, like
Is
if,
there any policy there? Or?
I mean, I hope not. I mean, we're a small team. We're, maybe like 6, 7 people. We're not like this dominant massive field, right? We're not Google, dominating NIPS every year, right? We're not DeepMind. So I think we're just trying to contribute tools that we can. I'm really excited by the fact that our code is all open. And so like when Dave and Alp and Rajesh and Dustin wanted to work on VB, they could come in and use our code and build it in, and we incorporated it. So I think we're very open to adding new tools that we can trust, and we can analyze and use it as a test bed for things. And we're not saying that there's other tools that aren't good.
Yeah.
Right.
No, I'm not talking about that, but
Yeah.
rather talking about what do you feel about like the field. Let's say let's say everyone uses Stan.
Yeah.
And somehow they are comfortable with using Stan
Yeah.
only, and then so much of the effort, research effort as a community is going to be biased toward the things that are well supported by Stan, right? Rather than the things that are, let's say, innovative or the very new. That
Yeah,
are not
yeah.
supported by Stan. So what do you think about just like?
Yeah, I mean, again, the best that I think I can offer is that we're not actually trying to discourage other people from trying things and going out in the community. I mean, if there's errors, if there's potential pathologies, we'll argue about the back and forth of these. But I think Dan's the one who's more than anyone says, in 10 years there may be no Stan, right? We might be done. And I don't think we're necessarily against that. If something better comes along, that's great. But our code's open source. It's all open on GitHub. Anybody can take it. Anybody can run it. And so even if HMC isn't going to be the ultimate answer, autodiff might be, right? So whether our modeling languages, our probabilistic programming language is useful, our autodiff is useful, our computational library is useful, or HMC is useful, take any of them. We're happy if you can use any of them for anything. So we're trying to really push this open science perspective. Yeah.
So just for the posterior density,
Yes.
You estimate high dimensional, just the way particularly with span search
Yeah.
space, would you be able to provide more intelligent summary of posterior distribution? 'Cause, oftentimes it's hard to detect multimodal.
Yeah. So I mean, well, I can show you.
Just the insights, right? How this algorithm is completed.
Yeah, I mean, it's tricky in the, sorry, let's see if I have this movie. I mean, there's novel visualizations that we can look towards. I'm not confident that any of them are going to provide substantially better intuition as to what's going on, because in the end, it's all about these expectations. It's just, so I'm not sure if there's anything immediately coming down the line. So at this time, I don't know. A lot of pretty pictures to do, to look at. In fact, I'll just end on a pretty picture then. Just a set of movies.
I mean, I had a question.
Yeah. So I'm just gonna put this in the background and then. Is that going? This is odd. Okay, sorry. Oh, I'm gonna.
Yes, so can you tell us a little bit about what are some application areas that you're particularly excited about that you think you might want to work on over the next couple of years?
Yeah, so whoops. Everything? I'm particularly, sorry. It's 30 seconds. I'll show you the movie in a sec. Yeah, so these are the kind of things that we could start doing that may be useful for visualization. I think they're useful for just like selling your model as being really cool and pretty. I'm not sure if there's qualitative use yet, but potentially. Sorry? No, I was answering Yang. Sorry, I just love those movies. So I originally come from physics. I love physics applications because that's what I got into this for, because I was the grad student, didn't know what they were doing. I want to go help past me's. But one of the things it's been really, really a pleasure is that with Stan, I've been able to work on things I never would have thought about working on. So like this malaria analysis, I hosted a workshop. I started talking with one of the postdocs, and we just went with it. So the real utility of having something like Stan is just anybody who's got a scientific problem, it's a potential collaboration, whether it's social science or pharmacology. Pharma is another big one that we work with. So I think at this point, I don't have a particular, I'm not trying to solve learn about the universe or solve malaria, or, I don't think in particular. I just want to get out there and solve as much science as we can. And being open, I think, is a real benefit given the just amount of problems out there. So science in particular, but really any interesting problem with interesting data, or people are just like, I want to be Bayesian, let's fit this. That's, I think, my wheelhouse.
I think we can
Cheers.